Hello, we will start this discussion on Chapter 3, Foundation of the Scalar Diffraction Theory. Chapter 3 has these contents: historical introduction from vector to scalar theory, some mathematical preliminaries, and then the Kirchhoff formulation and the Rayleigh-Sommerfeld formulation of the diffractions. So we will discuss some of the early chapters of the early sections of the chapter 3. Diffraction is known to be the bending of light rays that takes place when they pass through a region in which there is a gradient of the local velocity of a propagation of the wave. So, which means it is important to note that local velocity of a propagation of the wave changes, and then we have reflections. And in the case of reflections, light rays are bent at the metallic or dielectric interface, and the angle of reflection is always equal to the angle of incidence. We know all know those rules. When the light comes in, light reflect. There is the reflection, and this is refraction. This has been all known, and it is described in the ray optics. And then we all know that it is governed by the so-called Snell's law. But in the case of a diffraction, it is very different. Any deviation of the light rays from a rectilinear passage which cannot be interpreted as a deflection or refraction. So anything that is not either refraction or reflection is called diffractions. So diffraction is caused by the confinement of the lateral extent of a wave, and is most appreciable when that confinement is to the size comparable with the wavelengths of a radiation being used. So in the case of when there is some kind of aperture, and the size is, let's say, is A, and then when the light is coming in as a kind of a plane wave, and k vector is 2 pi over lambda, and lambda is very close to the A, then we have a very big impact of the diffractions. So if we have a certain aperture, that means if you know, think about the case, it is opaque, and then we have an open aperture, and it is not governed by this kind of ray optics. If it is really governed by ray optics, you can see that this kind of pattern without anything else. But in fact, we all know that there is a kind of a airy patterns like this in the screen, so that it is due to the diffraction. This is the very good example of diffractions. And this is the very proof that wave nature of light. So each point on the wavefront of disturbance were considered to be a new source of a secondary spherical wave, such that we have just wavefront coming in, and then each point of a wavefront is in fact a kind of a light source or point-like source. That is uh, the main idea we keep in the diffraction theory. So we call it Huygens principle. So when we have a certain aperture, and then we have this kind of light coming in, and then it is blocked, then we can think that each point here works as a kind of a light source, point-like source, and then it emits a point-like source everywhere within the aperture. So, and then this interference is acting as the main cause of the diffraction. So now it's time to think about the scalar diffraction theory. Remember that we are dealing with a scalar diffraction theory, but we all know that the electromagnetic wave is actually vector quantity. So in the case of a dielectric medium, then we have a electric field vector, H is the magnetic field, and electric field and the magnetic field is governed by the material characteristic, which is given by mu and epsilon. And mu and epsilon is the characteristics of the medium in which the wave is propagating. Okay. So, and we all know that electric field vector and magnetic field vector are a function of both the position p and time, so the space-time. And then we are going to assume that the medium is isotropic. That means there's no direction dependence, it's homogeneous, and non-dispersive, and non-magnetic. Okay, so this is the very important assumption we are going to keep. So non-magnetic means we do not consider mu, and that it is given by mu0. And non-dispersive means epsilon is a constant. Okay. And then when we decompose this Maxwell's equation, and then we end up with these wave equations for all components of E and H. And then this is the starting point of a scalar diffraction theory. Here, small u represents the scalar field component. It could be anything of the Ex, Ey, Ez, or Hx, Sy, Hc. Okay. So if aperture has an area that is large compared with the wavelengths, the coupling effects of boundary condition on E and H field will be very small, such that the boundary condition is independent, is not coupled, so that boundary condition only works for the electric field and magnetic field, and there is no cross terms. Okay. The scalar theory is accurate provided that diffracting structures are large compared with the wavelengths of light. So what we are going to do is that we are going to replace vector quantity by this mu, u. This vector is changed into u, and we think that once you know the u by solving this wave equation, then we can find out E and H. Okay, so this is the starting point of so-called scalar diffraction theory. What I mean by scalar means it's a scalar component, scalar field component, U, okay, which is the component of E and H vector. So from now on, we are not going to solve E and H because E component and H component both satisfies these wave equations. And once we know the wave equations solutions along with the given boundary conditions, then we know what they are. Okay. And now it's time to think about some of the assumptions. So we know that our scalar field component has a position dependence and a time dependence. And for the time being, we are going to assume that monochromatic. That means we have only single frequency, nu. And then we have a phase, and then we have an amplitude. Okay. Note that both amplitude and the phase are position dependent. Okay. And note that nu doesn't change. Nu is a constant. So if we rearrange this one, then we can see that in complex form, u is given by amplitude times time dependence. Note that this is the u. And then we have a complex amplitude, capital U, and it is nothing but these factors. Okay? And then when we put these equations into wave equations here, then the time dependence will kick out, and then we get this one. And this is called Helmholtz equation, as we know. And the k is termed as the wave number, and it is related with the wavelengths. Okay? And the wavelengths in the dielectric medium. Or you can say that 2 pi n over lambda 0. Lambda 0 is vacuum wavelengths. Note that n is the diffractive index of the medium. Okay, so we end up with these Helmholtz equations. So we have Maxwell's equations for E and H, and then we end up with the wave equations for small u, and for monochromatic wave, we have this Newton term, and then we get these Helmholtz equations. So note that Maxwell's equation for the vector component and wave equation for the scalar field component, and then we have this Helmholtz equation for the amplitude. Okay, and now it's time to think about how we find u. Okay, this is the things. So here is the Green theorem. So this is the Green theorem. And then what we want to know is that the complex disturbance u at an observation point in space. Okay, so observation point P. So we want to find out field scalar component u and its amplitude term. And I have already taken out e to the I 2 pi nu t term, assuming monochromatic radiation. And then the only left over is the amplitude term. And then here's the very interesting situations. So let u and g be any two complex valued function of position, and let S be a closed surface surrounding a volume V, and then inside S and B there is a position P. Okay, if U, G, and their first and second partial derivatives are single valued and continuous within on S, then we have this relationship. Okay, so this, if you look at it, this is the volume integral, and it's changed into surface integral. Okay. So note that this volume integral is changed into surface integral such that we have any volume, and then the surface on the outside, and it is enclosed by enclosing the volume inside. Okay, so that's the thing you need to know. And this Green's theorem is the prime foundation of a scalar diffraction theory. So if you look at it, there's a Laplacian G and Laplacian U. And if you go back, Laplacian plus k square, U should be 0. Okay, so there should be some kind of link between the Helmholtz equations and the Green's functions. So let's go back what we have done. So there's a Maxwell's equations for E and H. And then we have a wave equations for small u, p, t, and then for monochromatic wave, then we have u is the amplitude of small u, and then we have a Helmholtz equations. Is 0, and then on the top of it we have this Green's theorem. So there must be something, this Helmholtz equations and the Green's theorem, and that's the starting point of our scalar diffraction theory. Okay. So let P0 the point of observation, and S be an arbitrary closed surface surrounding P0. So here is the case. So here is our observation point, and then we have a surface enclosing P0, and then there is something else, which is S epsilon. So S epsilon has a radius of epsilon, and it is also enclosing this one. But this sphere is actually excluding P0, such that there would be no divergent component in the integrations. So for the case of SE, epsilon, and S, and its enclosed volume V prime, every function is going to be continuous and differentiable. So what we are going to do is that we are going to check out the G, Green's function. So remember that this is the Green's functions, and then we can choose one of the two functions, the U or G, for known solution of our Helmholtz equations, okay, so, or Green's functions. So in this case, the free space Green's function for Helmholtz equation is actually the spherical wave. Okay, so this is the very important statement, but for those who do not know, if there's any operators, okay, and then if there is a Green's function, and then we get this is the Green's function. So if you have a certain, any type of differential operators, and then there must be, there exists there could exist the Green's functions that satisfy this relationship. So if x prime is not equal to x, then this is going to be 0. Okay. So in the special case, when there is no boundary, free space, and when we think about these differential operators, and then we have g, and then we get 0. So Green's function is a solution of these Helmholtz equations. So here note that GP1 is given by R01, R01. R01 is point from P0 to P1. So there is some P0 vector, and then there is another P1 vector here. Okay. So note that Green's function should have two vectors. Okay. So if P0 and P1 is not identical, then it satisfies this one. Okay. So what we do know is that in the case of a Green's function, so we have a unknown g, unknown u, and g is known. And this satisfies Green's theorem. And then we can utilize this Green theorem to find out u for known g. Okay. So we have the total closed surface is given by s plus s epsilon, like this, and the inside volume is b prime. Okay. So note that the radius here is epsilon, which is very small. So now let's go back. We have these Helmholtz equations. And we note that G is one of the solutions. So note that P0 is not P1. Okay. And then if we apply this one, and we also know that U is also 0. Okay. And then our Laplacian is changed into k square G, k square U. Okay. And then our volume integral is going to be like this. And then the theorem reduced to like this. Okay. I hope you would understand this. Okay. And then finally, what we can get is the for the known G, and we have found out in the case of a small spherical surface S epsilon is given by this one, and is given by this one, and for S prime, note that we have a outside S and inside S epsilon, and general solution is given by this one, and the derivative is this one. Okay. And then what we end up with is that the surface integral for the small sphere is going to be if you look at it, it's going to be like this and this. And this is surface integral is nothing but 4 pi epsilon square, which is the surface of the sphere. And then epsilon square, and 1 over epsilon. And then as epsilon goes to 0, then this term goes away, and then only this term survives. And if epsilon is 0, this term is 1. And then we end up with this up0. And then what we have here is that we have a surface integral for s epsilon and surface integral for the outer surface is have this relationship. Okay, and if you look at it, we are trying to find out up0, and up0 is given by surface integral that is surrounding p0, and then it is given by this surface integral. And this integral theorem of Helmholtz over Kirchhoff, we call it, and this is the starting point of diffraction theory. Yet, this is the p0 that we want to know, and we are assuming that on the surface S, this value and this value should be known, and then we can find out this unknown up0. Okay, then this is the on surface, so that means field on the surface will determine the up0 that is enclosed by this one. Okay, so this is the result of Helmholtz equations and Green theorem, and then this will give you Helmholtz Kirchhoff. So what I'd like to tell you is that you don't have to derive whole things, but the important thing is that you need to follow the logic. Okay, so starting from the Maxwell's equations and then wave equations, and then Helmholtz equations and the Green theorem, and then we end up with the Helmholtz Kirchhoff. Okay, and do we have still more to go? Yes, we do. Okay, so here is the case. This is the S epsilon, and the B prime, and this is the what we have found here. Okay. Now it's time to change our S like this. This is our P0, and this is the screen. That means there is no field behind, and then there is aperture. So in this case, we have a S1 and S2. S2 has a radius of R, and S1 is enclosing the aperture. Okay, so what we would like to know furthermore is that for the given aperture, how we can get the scalar field component at P0. Okay, how they are related. So this is the question we are going to ask. Okay, so now we are going to talk about planar screen. So this is our screen here. Okay. And then our surface is given by S1 plus S2. S1 is that is enclosing our aperture, and S2 is kind of a sphere. Okay. And then we know that this is given by our Green's function for the Helmholtz is given by this spherical wave. Okay. And then what we know is that we are going to assume that the R is going to go to the infinity. So that means this radius is going to increase and increase and like this. Okay. And what's going to happen? Okay. So with the some of the assumptions, and then we end up with this kind of a relationship such that so as R goes to the infinity, S2 becomes like this, and then it's going to be 0. Okay, so basically the both G and U will fall off 1 over R. Okay, and then if you take the 1 over the derivative, then it is once again it is 1 over R cubed, and then we have this R squared, such that if R goes to the infinity, whole thing goes to 1 over R, and it should be 0. Okay. And in the case of these assumptions, we have this requirement: R times round over round n minus jku should be 0. And this is requirement is Sommerfeld radiation conditions. And this integral over S2 will yield a contribution of precisely 0 if these Sommerfeld radiation conditions are met. Okay. So once again, what we are doing here is that we start with the surface integral of S1 plus S2, but as R goes to infinity, we end up with only S1. Okay. But we are going to assume is that in this area, we are going to assume that the field component is 0 because it is shadow, right? And then we have this S1, only S1 comes in. And then the major contribution to the integral arises from the point of S1 located within the aperture sigma. Okay. And then we have another conditions. Kirchhoff boundary condition is that across the aperture, the field distribution and its derivative are exactly same as they would be in the absence of the screen. So this is the one of the assumptions of the portion of S1 that lies in the geometric field shadow of the screen. The field distribution U and its derivative are identically 0. We have these two assumptions, which is quite strong. And then our equations is now changed into surface integral over the aperture. Okay. So what it means is that our scalar field at the P0 is given by surface integral over aperture for these functions. Okay, G is known and the U should be given at the aperture. Okay. In order to have these equations, we have some of assumptions, and if the dimensions of the aperture are large compared with the wavelengths, and then we may have this relationship. But anyway, it is important to note that our scalar field is governed by surface integral of the field on aperture. Okay, so this is the very important information. And to further simplification, our scalar field component is obtained by this relationship, which is k is, remember that 2 pi over lambda, so that our wavelength is much smaller than our distance. Okay, and then these two assumptions are given, and then we have this relationship. So everything is given by known function. This is a boundary. Round U over round M on S and U on S. Okay, and then once you know this, and then we can find out the unknown by integrating over aperture. Okay, so this is the important case. So we further assume that our field is actually coming from point-like source at P2. Okay, so UP1, then single spherical wave like this. Okay, and then this is what we know at this aperture plane, position P1. Okay, this is what we know. And then in this case, our UP0 is given by this one. And illumination consisting of a single point source is known as a Fresnel-Kirchhoff diffraction formula. Okay, so everything is known. Everything is known. And then what we need to do is just to get the integral of the arbitrary aperture. Okay, so that the problem in principle can be solved. Okay. This 3.27 can be interpreted as this one. Okay. So our scalar field is actually, note that this is the spherical wave, which start from the aperture, and this is the kind of a amplitude on the aperture. Okay. So it is nothing but Huygens principle. So that means our diffraction pattern from an aperture is actually summation of point-like source, spherical wave, on every position on the aperture. Okay, that's the integral. Okay, so this is the Huygens principle. So we have these things, and then just read this one. And what is important thing is that so in this case, this is the important one. By choosing one of the Green's function as this one, G minus, and then we get very important formula. So in this case, only what we have to do is that we have to know only the U value on S, and then we can find out our scalar field. And but if we choose other solutions like a G plus, and then U2 P naught is given by this one, Yes. Okay, so the key thing is that in the Huygens-Kirchhoff theorem, we have to know we have to know both uh, derivative, normal derivative, and its value on the surface, okay? But it's not easy. Usually, you have information either on this u or that, okay? So, Rayleigh-Sommerfeld come up with this Green's function, and then you get these solutions, which require only the knowledge of normal derivative on the surface and, in fact, aperture. And in the case of U2, and so let me just try to tell you the things. Okay, so general is, for all cases, we can write UP0, our scalar component at the given position P0 is given by integral on the aperture with these functions. Okay. And then depending upon the choice, we have a term C, psi, and then it could be this. Okay. So for the special cases of an infinite distant point source, and then we have these three cases. Okay. So in general, what you can say is that this is the most general Rayleigh-Sommerfeld solutions, and that Huygens Prehlen's principle, is the important, physically very important one. Okay, so the observed field at UP0 is a superposition of diverging spherical waves originating from the secondary source located at each and every point P1 within the aperture. Okay. I'm sorry, this should be this one. Okay. Spherical wave and its weight over aperture, and the cosine theta is the directional compensations. Okay. And furthermore, we can see that UP0 is given by this one, UP1. This is input, output, and this is impulse response. Okay, impulse response in this case is given by this one. So we are going to consider this thing a little bit more in the chapter 4, but we'll stop here. Okay.